Welcome back to chemistry. And so what I want to talk about now is we were previously looking at the energies required to break covalent bonds to release the atoms from molecules. And so the energies required to do that are called bond energies or bond dissociation energies. So now we're going to switch to ionic compounds. And so as you might imagine, you can look at how much energy is required to break ions in the solid form and release them into free ions into space. You can look at that way. But what we're going to look at instead, and maybe more important, is the energy released when you take ions in space and you bring them together to have the ions stick together to form a solid compound. That energy that is released in that process is called lattice energy. So to introduce that, let me kind of make a few notes here to sort of compare bond energy of covalent bonds to lattice energies of ionic bonds. Okay, so let's say, again, what we learned last time is, let's say we have a molecule and it's held together with a covalent bond. And let's say this molecule has one atom of X and a different atom of Y. And so this is a molecule here. And the bond here holding the atoms together is a covalent one. And so what we learn is that you need to add energy to this molecule to break this bond to release the atoms, and so they go off into space. So I can represent that by putting an X and Y here, showing the separated atoms, and then just to point out that energy is required in this process. And so that energy required to break this particular bond is called a bond energy or a bond dissociation energy for the molecule. Now, one thing to point out, and I think you can sort of see at this point that this is an endothermic process. Okay, now kind of like I was saying before, if you have the free atoms in space and you were to bring them together to form a covalent bond, this is sort of the opposite process. And so if you take free atoms, they have relatively high potential energy, but when they're bonded together, they have relatively low potential energy, so that extra energy is released. And so in this process here, forming a molecule with bonds, this is going to be a very exothermic process. And basically, any energy needed to break this molecules into the separate atoms, that value of energy will be released if you take the separate atoms and form the molecule from it. Now, here, what we were doing is we were sort of giving the example of a molecule with covalent bonds. But now what we're going to do is look at a molecule with ionic bonds. And basically the same principles apply. So now, instead of looking, say, at atom X and atom Y, we're going to look at ion A, which we'll say is a cation, and then ion B, which is an anion. So let's say these ions are just kind of freely floating in space. If you were to bring them together to form the ionic compound AB, as you might expect, because these free ions, like the free atoms in the molecule, the free ions have high potential energy, and the ions bound together have low potential energy, then we would expect energy to be released here in this process. So whenever you take any kind of free ions, and I'm going to add state symbols here to indicate that they have to be in the gaseous state, and you bring them together and they stick together to form an ionic compound, which is now in the solid state, you will release a large amount of energy. This energy is called lattice energy. So why is it called that? Well, I think I can explain it best with this picture. So I have sort of an example here of the process of free ions here binding together to form a solid ionic compound. So maybe you can sort of think of the green dots as the positive cations and the red dots as the negative anions. And so they're out in space and they have relatively high potential energy. And so if you can get them to stick together, you will form this very nice ordered array of ions, which is the solid ionic compound, and you also release a lot of energy in the process. This ordered array of ions is called a lattice. So here, when you take these free ions and you get them to stick together to form an ordered lattice in the ionic salt, the energy released is called the lattice energy. So one of the things we have to sort of learn right now is we need to learn sort of what the trends in lattice energy are. In other words, when is it, what kind of particular ions do we need maybe to get a little bit of energy released when those ions get together to form the salt? And then maybe what are the different kind of ions that you need when they get together, maybe give you more energy release. So we're going to talk about that now. Okay, so let's look at this slide here. What we're looking at is at 4 different ionic compounds. And so one ionic compound is lithium chloride, another is sodium chloride, another is potassium chloride, and another is cesium chloride. And so what those values are that you see on the right, those values are the energies that are released when you take those free ions and you bring them together to form the solid compound. And so what I want you to see is that as we go down this list of solid ionic compounds, that it looks like the amount, the magnitude of energy released is getting less and less. Now, there's a negative sign with all of them, and that sort of indicates that this is process where you take free ions and you stick them together to form the salt is going to be an exothermic process. But again, as you go down the chart, the values get less and less. And so you need to understand why that is going on. The reason why that is going on, it has to do with how close the ions can get to one another in the solid compound. The rule is this: if the ions can get close together in the solid compound, when you form the solid compound, you're going to release more energy. So if you look at that sort of those pictures there, the top pair of ions there is lithium chloride. The next pair is sodium chloride, then potassium chloride, then cesium chloride. Now notice they all have the chloride anion, so that is not changing in these pictures. But what is changing is the size of the cation. I want you to notice that the lithium cation is much smaller than the other cations. And so that allows it to bond to the chloride anion nucleus much closer than the other cations. And so you can sort of see the distance between the lithium cation nucleus and the chloride anion nucleus to be 241 picometers. Now, when you go to the sodium ion, you can see it's a larger ion. So because of that, it sort of shoves the sodium positive nucleus a little further away than the chloride anion nucleus. And so the distance between those ions is a little bit larger. And then you can just keep going down. And then by the time you get to the cesium cation, it's such a large cation that it's kind of far away from the chloride anion. And so it has a relatively large distance between the ions, which is 348 picometers. And so what you can sort of see is that the smaller the distance between the ions, the more energy that is released. And so you sort of need to understand why that is the case. And so remember I was talking a little bit about Coulomb's law in a previous class. And so there was one formula I gave for Coulomb's law where we're trying to find the force between ions. And so force was using the variable F. And that equation was F equals K times Q1 times Q2 over R squared. Now here you can sort of change Coulomb's law a little bit and look at the energy that can be found between ions. And so you can sort of modify Coulomb's law, change it from force to solving it for energy between ions. And so when you do that, the law you get is E, which is energy, is equal to the constant K, Q1, Q2 over R. So what is Q1? Q1 is the magnitude of one of the charges, say the cation. Q2 is the magnitude of the other charge, say the anion, and R is the distance between the cation and the anion when they're bound together. So here, what we're doing is you look carefully at the charges of these ions. The chloride ions are always a single negative charge. So we'll say that Q2, its value would be -1. The charge of the cations is also always +1. So the value of Q1 will be +1. Now, what is R? So R is the distance between the cations. And what I'm kind of hoping you'll notice is here in this equation here, there's R in the denominator. Imagine what happens if the value of R, the distance between the anion and the cation, gets smaller and smaller and smaller. What's going to happen to E? The value of E will increase. So the reason why, as you go from cesium ion to potassium ion to sodium ion to lithium ion, you're releasing more and more energy when those ions stick together to form a solid, is because those ions can get closer together in the salt. If you throw that information into Coulomb's law, we would expect more energy to be released. Okay, so that is one trend you need to know. And so the next trend you need to know is you need to sort of understand what is the difference in energies released when you, say, have a cation with a single positive charge bonding to an anion with a single negative charge versus a cation with two positive charges bonding to an anion with two negative charges. Here we have a wonderful example. We have sodium bound to fluoride ion. And what you can see is that if you take those two ions and they're in the gaseous state and you bind them together to form the crystal lattice, it will release energy. And the amount of energy that will be released is 910 kilojoules per mole, and it's a negative sign, so this again indicates the energy is released. And so we see a nice picture there, and the sodium cation is a certain distance away from the fluoride anion. It's about 231 picometers away. Now, compare that to the lower picture. Here, the cations and anions are different. We have a calcium cation bound to an oxygen anion. And I want you to notice that the calcium cation is not +1, it's +2 charge. The oxygen anion is -2 charged. Now I want you to notice that the calcium cation is bound at the same distance, approximately, to the oxygen anion as sodium is bound to fluoride. So sodium bound to fluoride is about 231 picometers between the nuclei of the ions. But calcium oxygen is about the same distance. Despite that fact, if you have sodium and fluoride ions sticking together, they will release a certain amount of energy, 910 kilojoules per mole. But with the 2+ and 2- ions, it releases nearly 4 times the amount of energy. It's going to be 3,414 kilojoules per mole. So the question is why? And so we can sort of understand that again by looking at Coulomb's law. And so here it is again, we're looking at the energy form because we're solving it for energy. It's going to be equal to a constant K times the magnitude of the charge of the cation, which would be Q1, times the magnitude of the charge of the anion, which is Q2, divided by R. So looking at these two examples, they have the same distance approximately between the cation and the anion. So the value of R isn't the same. So that cannot account for the difference in energy that we're going to get between these two situations. So what can? Well, here's the deal. When you have a sodium positive charge, it is 1 positive charge, so I'll put a 1 there. Here, if you have a fluoride positive charge, it has a 1 charge. So the value of Q1 will be 1, the value of Q2 will be 1. Now let's look at calcium and oxygen. The value of the calcium charge is 2, while the value of the oxygen charge is 2. So what you can sort of see is the way you derive the energy from these ions is you have to multiply the magnitudes of the charges together. So what you can see is when you multiply the sodium and the fluoride charge are 1 apiece, 1 times 1 is 1. But if you multiply the charge magnitudes of the calcium oxygen, it's 2 times 2, which is 4. And so it's a larger number, and so you're going to get 4 times the energy released when calcium and oxygen bind together as opposed to sodium and fluoride. Okay, so the thing to sort of know here is that when you increase the amount or magnitude of the charges of ions binding together, generally that means is that you're going to have more energy released as lattice energy. Okay, so there's the final question here. So this is sort of a nice test question. It says, order the following ionic compounds by increasing magnitude of lattice energy. And so we have several compounds here. And so one compound here is calcium oxide, one compound is potassium bromide, then potassium chloride, and then strontium oxide. And so what we have to do is figure out, of those compounds, which has the least amount of energy released when it's formed from its gaseous ions. What's the next up? What's the next up? And then which will have the most amount of energy released when its ions bind together. And so there's a sort of a strategy here that is given, which is helpful. It says, first examine the ion charges and order them by sum of the charges. Okay, so one of the things you can sort of notice there is that we have, in the example of calcium binding to the oxide anion, so calcium is a 2+ and oxygen is 2-. And so that adds up to 4 total charge units. And so potassium and bromine is 1 apiece, so that's 2 total charge units. Potassium chloride is 2 charge units, and then strontium oxygen is 4 charge units. And so one of the things you can immediately do is we know from the previous example that when you have ions that have more magnitude of charge, when they bind together, they'll release a lot more energy. And so we can put the ones with the larger sums, which are calcium oxide and strontium oxide, we can know immediately that they will definitely have greater lattice energies than the other 2 salts, potassium bromide and potassium chloride. So we've done that sort of this step here. And so we're just indicating at this point, we understand that the ions with the greater magnitude of charge will have the greater lattice energy. But now we have to go a little bit further. We sort of have to order those compounds within each case and put them in the right order. And so here what you sort of have to remember is the sizes of the ions. And that can be a little bit difficult, but what you'll have to remember is this. Let's say you're bringing in pairs of ions. In all the cases, all the ions have a single charge. You might remember if the ions are larger, they can't get as close to one another when they form the lattice, and so they won't release as much energy. But if the ions are smaller, they can get closer to one another in the lattice, and so they will release more energy. So what you're going to have to do is sort of remember, okay, between potassium bromide and potassium chloride, they're both potassium ions. One is a bromide anion and one is a chloride anion. Can you figure out which one's smaller and which one's larger? The one that is larger, that salt, will have less energy. The one that is smaller will have more energy. And so you might recall that bromine is below chlorine in the periodic table. And so if that is the case, bromine will be a larger anion. And so bromine is a larger anion compared to chlorine. They're both binding to the potassium anion. Bromine, because it's the larger anion, cannot get as close to potassium as chlorine, and so it will release the least amount of energy, the last energy. Now, you're going to have to order strontium oxide and calcium oxide. You basically use a similar argument. So you might remember that strontium is lower in the periodic table than calcium. They're in the same group, group 2, but the strontium is a little bit below calcium. And so strontium is going to be further away from the oxygen than calcium would be. And so if strontium is further away, when it forms the lattice, it will release less energy than calcium oxide. And so that should give you the final order. So thank you for listening to that, and we will see you next time.